Hello class, today's lesson is 4-5 in your textbook, titled How to Prove that Triangles Are Congruent by SAS and HL. Okay, these are going to be two new things that are going to help us out with our triangle congruence that we've been working on. The first one is SAS, it's postulate 20, and it stands for side angle side. Okay, and what it says is that if two sides and the included angle of one triangle, so that means this angle that's included in between those two sides, and two sides and the included triangle of another triangle are congruent to one another, then the two triangles are congruent. So if I was going to write this out, the things that I need to be looking for are if, let's say, RT is congruent to UW, that's one of the sides, and also angle R, if that is congruent to angle U, that's the angle that's right in the middle of the two sides, and also if side RS is congruent to side UV. If I have all three of those things, then I can say that triangle RST is congruent to triangle UVW. Okay, so let's go ahead and do a example proof based on this idea. It says to prove that ABC is congruent to triangle CDA. So this is ABC in that order to CDA. Okay, and what I'm given is that these two sides already have markings on it to show me their congruence, and both of those sides also have this extra arrow which is telling me that BC is parallel to AD. So let's just write some of those things that we can see from our diagram that were given in the beginning. So as I said, BC is congruent to AD. That's given. Okay, and I also said that BC is parallel to AD. That's also given from the markings. Okay, so right now all that I have is one side. I'm looking for an angle now if I want to use SAS, and I can see because these two lines are parallel that this angle right here, BCA, and this angle right here, DAC, are congruent. So BCA is congruent to angle DAC, and that's because of the alternate interior angles theorem. Alternate interior angles theorem. Okay, which meant that the alternate interior angles, when you have two parallel lines, that they are congruent. So I have my angle, I'm looking for one more side, and I can see right here that AC is shared in both of those triangles. So I can say side AC is congruent to side CA by the reflexive property of congruence. So I have found a side, an angle, and a side that's congruent to another side, angle, and side. So I can conclude then that triangle ABC is congruent to triangle CDA because of the side, angle, side postulate. Okay, awesome. So we were looking at an angle, we called it the included angle, where it was in the middle of the two sides. So I have a question for you. Can the one congruent angle be somewhere else? So in this example right here, I kind of color-coded to show that these two blue lines were the same length. I think I measured them at 4 centimeters. And these two purple colored sides were about 3 centimeters each. Okay. So I'm wondering, is it possible that the angle doesn't have to be in between the blue and the purple? Well, as you can kind of tell, just because it has one congruent angle doesn't necessarily mean that the two triangles themselves are congruent. We can kind of see that this first one is smaller already. So the answer is no. And then I'm going to put except. There is one instance where it will work, okay? And that only instance is with a right triangle, okay? And so in a right triangle, I know that the two sides that are touching the right angle are called the legs, and that this more diagonal side across from the right angle is called the hypotenuse. So I have a theorem, 4.5, called the HL, or the hypotenuse leg congruence theorem. And it says if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and leg of a second right angle, then the two triangles are congruent. Okay, so in this case it kind of looks like SSA. I'm not going to say it backwards. I think you know why. But SSA, a side, another angle, will only work for right triangles. And so that's why we're calling it the HL, the hypotenuse leg congruence theorem. So we're always reminded that it's only for two right triangles. Okay, so let's do an example based on this then. Okay. In this example, I am given a picture like so. Okay. And I'm told that WY is congruent to XZ. So WY, this long side, is congruent to XZ. Okay. I'm also told that WZ, this side right here, is perpendicular to ZY, and that XY is perpendicular to ZY as well. And I want to prove that these two triangles are congruent to one another. So what I would say first in an example like this is to just redraw the picture so that they're not overlapping. Okay. So the triangle WYZ is going to look the same, but this other one up above, I'm just going to flip it over. I'm going to do a reflection, and I'm going to label those points. And so from what I'm told in the beginning, I was told that WY, that this side right here, is congruent to XZ. Okay, and then I'm also told that WZ is perpendicular to ZY, which means that that's going to be a right angle right there, and that XY is perpendicular to ZY, so that's also a right angle. So I'm looking for one more thing. Okay, so I have this kind of rewritten now, so let's go ahead and do our proof. Okay, so we redrew the picture so it's a little more clear for us to look at, and let's just go with what we know. So we know that WY is congruent to XZ. This was something that we were given at the very beginning, and then we went ahead and we kind of made that apparent in our diagram. We are also told that WZ was perpendicular to ZY, and we are also told that XY was perpendicular to ZY. This was something else that we were given at the very beginning. Okay. And then, because I know that those were perpendicular, I went ahead and I drew those right angles, because I know that from the definition of perpendicular lines, that they meet at a right angle. So that means that angle Z and also angle Y are right angles. Okay, and this is just the definition of perpendicular lines. Okay, we're almost done. Let's see, what's next? Well, I can say that this triangle, that would be triangle WYZ, and the other triangle XYZ are right triangles. And you might be wondering why I'm just claiming that fact. It's going to be important in just a moment. So this I can just say is from the definition of a right triangle. Okay, but it's something that I need for the HL for that theorem. So one more thing that I can claim, because I know the hypotenuses are congruent, I also know that they have a right angle. If I can find one more side, one of the legs to be congruent, then I can claim HL. And I can see here that they both share this bottom leg from the diagram up above. So I'm going to claim that down below. That ZY is congruent to YZ, again from the reflexive property of congruence. Okay, so then I'm going to end with claiming that triangle WYZ is congruent to triangle XZY because of the HL, the hypotenuse leg congruence theorem. And I'm done. Okay, so I hope that this has been a good outline for how you can organize any proofs that you're going to work on in class. So come with any questions you might have, and I'll see you then.